We're looking at induced EMF in a moving conductor. And to start with, we're just going to revise what happens to a charged particle. So I better change that to a D. A charged particle as it moves through a magnetic field. So we have this magnetic field that's moving from right to left. And we're going to place a positively charged particle, which has a velocity downwards, a velocity v. And so from the right hand rule, so we'll insert a hand over here. From the right hand rule, we know that the thumb is our direction of current, and in this case we're going to say it's the direction of our particle. Okay, so that's our direction particle, our velocity. We have our magnetic field, which is the fingers. So that's B. And then that tells us our direction of force would be the palm. So in this case, that would be going into the page. So that would be our direction of force. That would be pushing this positively charged particle into the page. Okay, so F in this case is, direction of F is into page. If we wanted to work out the magnitude of the force of this charged particle moving through a magnetic field, well, that would be force equals the size of the charge multiplied by the velocity multiplied by the strength of the magnetic field. And we can use this knowledge of a single charged particle moving through a magnetic field and apply it to a conductor that's in a magnetic field. So here we have a straight copper wire that's going to be moving down with velocity v through this magnetic field that's moving left to right, or sorry, right to left, which is B. And so the first thing I'm going to do is get my right hand rule out and just place that over here. Okay, so we can see that the magnetic field will be moving to the left. Our velocity of all the particles in the conductor is downwards, which means the direction of force for a positive particle will be into the page. Okay, and so what that means is as our conducting rod moves through the magnetic field, we are going to get an excess of positive charges into the page, and we will get an excess of electrons or negative charges coming out of the page. And this causes a potential difference. This actually creates a change in potential or a change in voltage. EMF is defined by the amount of work done per unit charge. So defined by work per unit charge. Okay, so we have epsilon is our symbol for EMF, equals work on charge. And we know that work, so since work equals force times displacement, and we know that the force on a charged particle in a magnetic field is QVB. Therefore, we have for EMF, epsilon equals force times displacement on charge, and force is the same as QVB. So therefore we have QVB times displacement over charge. And we can see that the two Q's, so the two charges, will cancel. And so we're left with epsilon equals V times the magnetic field times displacement. Now, in this case, our displacement is actually the length, so where S, so our displacement is the length of the conductor traveling through the magnetic field. In magnetic field in B. Okay, so therefore we are left with our electromotive force, so epsilon equals LV.